Plastic pollution is one of the most urgent challenges in the environment today. When larger plastics break apart due to natural processes such as UV exposure from the sun, they turn into microplastics. These are tiny fragments that are only a few micrometers long and that are extremely difficult to remove and are very harmful to marine ecosystems, wildlife, and even humans. Hi, we are Team 6, and our 169 project focuses on preventing microplastics from becoming microplastics in freshwater environments.
To address this growing problem, we have identified the need for a safe, affordable, and effective way to remove floating macroplastics before they have the chance to fragment into tinier microplastics. According to Science Direct, 69% to 81% of microplastics originate from larger plastic debris. So, removing the source itself is a more effective and executable engineering design problem than to just manually remove microplastics from the water sources we are targeting.
Microplastics are linked to ingestion by marine life and contamination of drinking water. Existing solutions like large floating boats are designed for large bodies of water, but not smaller lakes. That's why our teams designed a portable, autonomous robot. After researching and testing, we found a conveyor belt system, which is the most reliable.
We began to brainstorm over 20 ideas like nets, pumps, and porous carbon filters. We evaluated each based on safety, distribution to wildlife, and portability. Through screening and ranking, we eliminated ideas that were too expensive, complex, or unsafe. In our scoring stage, the conveyor belt robot scored consistently in the highest weighted decision matrix, even after the sensibility analysis due to the low cost, safety, and the portability.
Our final proposed solution is a macroplastic collection robot that floats on the surface of the water. It uses a rotating conveyor belt to lift debris out of the water, compacting it on board and storing it in a bin. We created multiple prototypes, showing the design process from a simple sketch, a physical 3D model, to a working belt design for testing debris collection. For the main functional test, we placed the belt into the water, submerged 1 inch deep at a 30-degree angle. Then small plastics are placed into the water that float on the surface ready to be picked up. The test criteria include the ratio of failed to pick up attempts to successful attempts.
This solution prevents plastic from the outside environment, thus reducing exposure to degradation, which directly slows down the formation of microplastic.
Now let's look at the cost and benefit analysis. For both physical prototypes, the 3D model and belt system, the materials were selected based on accessibility and adjustability. Starting with the wooden frame model, the materials consisted of popsicle sticks, toothpicks, hot glue, and skewers. These materials were already on hand for the group and made prototyping simple, effective, and allowed for more time to be focused on functionality of the third prototype. For the working belt system, Lego Technic parts were used to make a disassemblable and irritable isolated system. This design allows for submersion in water without risking water damage to metal parts or electronics, while accounting for the accessibility materials as one of our group members had the Lego on hand.
The functional test belt allows for a concrete visualization and the basis for iteration of the final product. These materials shows the necessity of having many moving parts working together for an efficient system to collect as much microplastic as possible. A major benefit of using Lego for the final test is the ability to be assembled for improvements.
While our prototype performs well in testing, one limitation is that it's optimized for controlled freshwater environments like ponds and lakes. In rougher conditions like high winds, it can reduce the robot's ability to guide plastics into the conveyor intake. However, most macroplastic accumulations happen in calm bodies of water, which our robot remains to the optimal solution rather than over-engineering the system for extreme weather conditions. We focus on environments where the prevention of macroplastics is most impactful.
In a world where microplastic pollution can pose such a detrimental effect, accessible prevention tools are becoming more valuable. Our robot is simple and scalable, working where the problem is most concentrated and doing so using low-cost components. But beyond the prototype itself, preventing plastic breakdown is one of the most effective ways to protect aquatic life and preserve water quality for future generations. The issue goes beyond a single prototype or design, as addressing microplastics is not just an engineering challenge, but it is a responsibility we all share.